Hello, I'm Simran Sangha, a PhD candidate from the University of California, Los Angeles, working in collaboration with David Beckert and Gareth Funning, and I'll be sharing work done towards a comprehensive statewide Sentinel-1 InSAR analysis, leveraging an operational archive of standard Sentinel-1 InSAR products hosted by the ARIA project from JPL. The existing ARIA archive includes products from 9 tracks of Sentinel-1, which span the entire state of California and which span back through late 2014. With these products, we use the open source packages ARIA tools and MintPy to pre-process and compute time series analysis, respectively. And we may also use ARIA tools to apply tropospheric corrections derived from the GEICOS project. These corrections reduce the impact of tropospheric noise at long wavelength spatial scales in order of around 100 kilometers. Illustrated here are line of sight InSAR surface velocities generated before and after applying tropospheric corrections, respectively. This is a fantastic data set where major tectonic features and subsidence are resolved through the entire state of California. For instance, you could see the creeping segments of the San Andreas Fault, which span the entire state of California. You could also resolve some large-scale hydrological signals focused in major basins such as the Central Valley. I'll take a closer look at some of these faults in the Bay Area shortly as well. First, for the most part, uncertainties associated with InSAR velocities are rather low, and you can see that the long wavelength errors are reduced after applying tropospheric corrections, which is anticipated. And there's also good agreement between InSAR and GNSS stations, but with some caveats, namely caveats which are better illustrated here to the right in figure 4, where we see scatter plots for each InSAR track representing comparisons of co-located InSAR and GNSS line of sight rates. So note that the track numbers for each of these plots is denoted at the top, and you could refer to the map to the left for reference to see where these tracks are situated. And black and red markers correspond to InSAR before and after tropospheric corrections were applied, respectively. You can see in some cases, such as for track 137 and track 64, there's these large GPS rates, which are significantly underestimated with respect to InSAR. And we believe that this is attributed to phase aliasing, where InSAR is underestimating the high subsidence rates in particular, which is concentrated again along some of the major California basins. Now let's look at some time series histories of the co-located GNSS and InSAR observations spanning descending track 42, where all observations have been referenced with respect to a single point denoted by the black square north of the Bay Area. Time series histories were selected adjacent to the Hayward Fault, San Gregorio Fault, and the San Andreas Faults, respectively. And InSAR and GNSS station displacements are denoted by blue and red markers, respectively. Each of these plots were taken from points along these dextral strike slip faults, so we can collect vertical motion vis-a-vis fault parallel motion. And since this is a descending track, negative or blue rates correspond to fault parallel motion away from the satellite. So inconspicuous right lateral motion along each of these fault segments is resolved and ranges from around 2 to 6 centimeters over 5 years, with steeper rates along the San Gregorio and San Andreas faults with respect to the selected reference point. And smaller inflections and cycles are resolved in both GNSS and InSAR, though more work is needed to investigate the sources of such signals. So we'll end on results in future work. So tropospheric corrections improve InSAR velocities at long wavelength spatial scales. Thus, we may better resolve major tectonic features and subsidence through the entire state of California. However, our current strategy of referencing InSAR fields to a single GNSS station appears to translate to some level of RMSE biases. So we plan to instead reference InSAR to GNSS through a minimization across the network. And furthermore, our analysis suggests InSAR significantly underestimates large rates of deformation, such as subsidence vis-a-vis GNSS due to aliasing of InSAR phase. And this work is performed in parallel with the other CGM efforts. We are now engaging to incorporate our work through the CGM archive. As far as future work goes, we plan to invert InSAR velocities for strain accumulation rates on the major faults of California. So perhaps stay posted at AGU this year. And you could see the full poster and other associated recordings at this link here.